Okay, let's look at the problem on slide 25 of chapter 3. And for this part, we're going to learn how to write electronic configurations in 3 different ways. This is called the diagram, the electronic diagram. We will learn the complete electron configuration notation and then the shortened or noble gas configuration shorthand notation as well. So let's start with the example of sodium. Sodium, the symbol is Na, and if we look it up in the periodic table, is number element 11. Now, as we said in chapter 2, the number in the periodic table is the Z number. It's the atomic number, and it tells us the number of protons. It also tells us the number of electrons for sodium atom. So this is 11 protons. It will also be 11 electrons. And these are what we're interested in right now because this is electronic configuration, which means we have to deal with electrons. Now, according to the rules that we just talked about in lecture, we will start filling out this diagram. And I don't expect you to memorize how to do this necessarily. I will show you how to fill this out. But in lecture, remember how we talked about which level, which period is filling what, and divide the periodic table into the 1s or the s orbitals, the p orbitals, or the d orbitals, etc., etc. It just is an easy tool to remember where you are in the periodic table. It's pretty cool. Okay, but let's look at sodium. And according to our rules, we will start from the lowest energy level first. Notice that on this axis over here, I have energy. So the lowest energy fills out first. It's increasing because I have an up arrow. The lowest energy fills out first, and then you can see how these, I have 1s first, then 2s. 2p is a little higher than 2s. 3s is higher than 2p. 3p is higher than 3s. Now note, 4s is higher than 3p, but is lower than 3d, so these will be filled first. Then we move to 3d, then to 4p. Okay, so let's look at aluminum. It has 11 electrons, so we start filling from the bottom one first, and we fill one at a time. So this is 1 electron, and we have to pair them. Okay, so starting from the lowest energy first, that's my off-bow principle, and then the Pauli exclusion principle tells me that each of these little lines here, each of these orbitals, they represent orbitals, can take 2 electrons. And then Hund's rule says that they have to, the spin has to match, okay? And then when we get to these orbitals here that have the same energy, we will put electrons, 1 electron in each first, and then come back to pair them up. But in this case, my 1s, I will put 1 electron, and then there aren't any other orbitals that are the same energy level as 1s, and therefore I have to come back and match that particular electron that I started. So I've used up 2 of my 11 electrons. Now I can start filling out the 2s, and I do the same thing. I fill 1 electron, but I'm not ready to put electrons in the 2p yet because I have to match the note that, remember that from the Pauli exclusion principle, that each of these lines will take 2 electrons. So I have 1, but I have to come back and match it with a spin down. So I have filled the 1s and the 2s. Each of these holds 2 electrons, so I've used 4 of my 11. I have 7 more. Now when I hit orbitals like the 2p, where I have 3 of these orbitals that have the same energy, right? They're at the same energy level, or I try to draw them exactly the same. I will populate each one of these with 1 electron first and then come back to match them. So I will put 1 electron here. That's 5. And then I still have electrons, so I keep going. That's 6. That's 7. Now that I put 1 in each, I can come back and pair them up. But you have to first put 1 electron in each orbital that's the same energy level. And then I can come back here and here, 9, and this is 10. So 2, 4, 6, 8, 10. However, I have 11 electrons, which means I have 1 more to put in the 3s here. And then I ran out of electrons, so I'm done. This is the energy diagram. Now there are two other ways, and you will have to know all 3 of them for the exam. So this is how we do the diagram. Now let's write the electronic configuration. Here's where I write all of the orbitals in order. So I start with the lowest one and then progress. And then I add how many electrons they each have. So 1s will have 2 electrons, and I put that as a superscript. 1s2. Then I move to the next orbital, which is 2s. 2s also has 2 electrons, so I'll put a 2 in front, or as a subscript over the s. And then I move to the 2p. 2p. The 2p has 2, 4, 6 electrons, so I'll put a 6 as a subscript. And then my last orbital is 3s, and I only have 1 electron there, so I put that. So this is the electronic configuration for sodium. This is the full electronic configuration. So this is full configuration. Now let's talk about the shorthand notation. The shorthand notation cuts off to the nearest noble gas configuration. The closest noble gas configuration to sodium, if you look in the periodic table, is the previous noble gas, which is neon. Okay, neon has 10 electrons, so it's right before sodium, which means that I have 2, 4, and 6 is 10. So up to here, this part corresponds to the neon configuration, because this is the configuration of neon with 10 electrons. And then the 1 more, so sodium is 1 after neon, so it has 1 more electron. That will be the configuration for sodium. But if I replace this one, which is the configuration for neon, by just writing neon, and then what's left over will be 3s1. These are similar. I mean, they're the same ones. I just replaced this configuration for the symbol of neon, because this is the configuration of neon. And this is the shorthand notation. When you do this, the electrons that are left over, right, the electrons that come after the noble gas configuration will give you the valence electrons. And these are important. The valence electrons are important because they tell us the chemistry of that particular element, in this case, sodium. Sodium has 1 valence electron. That's why it forms a +1 ion, because it loses that electron very easily to get to the neon configuration, which is the noble gas configuration. It's more stable that way than having that extra unpaired electron. Okay, I am going to erase this, and then we will do some more examples of electron configuration just to get the idea.